Hello everyone, I'm Janvi, currently studying at Northeastern University and I'm enrolled in the course Data Science and Engineering under Professor Akash Murthy. In this video, I'll be walking you through 6 key assignments where I have implemented and analyzed core machine learning concepts using generating modeling from VAEs to transformers. Let's dive into the first one. The first is elbow in VAEs and diffusion models. In variational autoencoders, the elbow or evidence lower bound is a way to train the model by balancing two terms, the likelihood, which encourages accurate reconstruction, and the KL divergence, which regularizes the latent space. In diffusion models, a similar elbow-like objective arises when reversing the noise process to learn how to generate realistic data. In both cases, elbow helps ensure that the model captures structure while staying close to the prior beliefs. This balance is what enables these models to generalize well in practice. The second one is beta VAE. The beta VAE introduces a scaling factor beta to the KL divergence term in the original elbow. This controls the trade-off between reconstruction accuracy and disentanglement of the latent variables. A higher beta forces the model to compress more information into the latent space, promoting better, but sometimes at the cost of fidelity. Tuning beta helps us discover interpretable and structured latent representations, which can be very useful in supervised learning. The third one is diffusion process in diffusion models. The diffusion model gradually adds noise to data in forward process and learn to reverse the noise in a step-by-step manner to generate new samples. This is grounded in stochastic differential equations and mimics a gradual denoising process. By learning the reverse path, the model generates high realistic data. The theoretical foundation ensures the learned distribution closely approximates the data distribution over multiple steps. The fourth is Gaussian VAE loss and reparameterization trick. In Gaussian VAEs, the loss combines reconstruction error and KL divergence. The reconstruction term ensures accurate outputs while the KL term regularizes the latent space. We use the reparameterization trick to allow gradient flow through stochastic nodes. This means sampling is done using a deterministic function of noise, enabling end-to-end training. This technique is key optimizing VAE efficiently. The fifth one is, throughout this course, we have studied foundational papers and shaped modern generative AI. The first one was autoencoding variational Bayes, which introduced VAEs combining deep learning with variational inference to learn meaningful latent representation. Then the second one is generative adversarial nets by Goodfellow proposed GANs, where a generator and a discriminator compete, leading to highly realistic sample generation. We explored DDPM or denoising diffusion probabilistic models by Ho et al., which presented a novel approach to data generation using a gradual denoising process, enabling state-of-the-art result in image synthesis. Beta VAE is the fourth research paper, which is the VAE framework by encouraging disentangled latent feature, improving interpretability. And finally, attention is all you need by Vaswani et al. Introduced transformers, eliminating recurrence and using attention mechanisms to model sequences efficiently. Each of these papers taught me not to just how generative model work, but why they matter and how each method offers a different trade-off between structure, control, and realism. The sixth question was about reflection of learning GANs, VAE, diffusion model, transformers. So learning these models gave me a deep understanding of how machines generate data from image to text. It expanded my thinking on unsupervised learning and the different techniques each model uses to capture complex data patterns. I intend to apply these skills in research or industry projects related to generative AI, especially in image synthesis and representation learning. That's all about the assignment. Thank you.